Welcome back to Honors Calculus. In this video, we're going to be looking at combining functions. There are any number of different ways that you can combine two functions. Two of them are of specific importance in our study of calculus. The linear combination is one of those, it's so straightforward, why did we even bother giving it a name? Until we get through and find out that linear combinations are the most well-behaved thing in everything we do in calculus. Anyone who is moving on to study linear algebra at some point in the future, that is an entire course devoted to things that behave nicely around linear combinations. The other thing that we can use is function composition. You've probably seen function composition in a previous course when you were talking about the inverse of a function. We're not going to be looking at inverse functions in this course, but we are going to look at a couple of other things that function composition can do to our advantage. So let me get my head out of the way and let's dive right in. So if we let f and g be any two functions, and we let a and b be any two constants, then a linear combination of f and g is any function h, which can be written as a times f plus b times g. That is incredibly vague. For example, the function h of x equals 2x plus 3 is a linear combination of f of x equals x and g of x equals 1. Specifically, it's 2 times f of x plus 3 times g of x. Very, very straightforward. For something a little bit more complicated, if I'm looking at h of x equals 4x squared plus 6x minus 7 times the cosine of 3x, that is a bit of a mess. But this is, again, the linear combination of a couple of functions. It's actually the linear combination of 3 functions, but I'm going to call it the linear combination of 2 functions. Specifically, if I define f of x equals 2x squared plus 3x and g of x equals the cosine of 3x, then h of x is 2 times f of x minus 7 times g of x. That is one of a number of different options that we can use to write this as a linear combination of 2 functions. I could have just gone ahead and called f of x 4x squared minus 6x. I could have called g of x the negative of cosine of x. I could have called it 7 times the cosine of 3x. I could have called it 12 times the cosine of 3x, and then my constant would have been negative 7 over 12. Those are all perfectly valid. So linear combination of functions is a very generalized thing. And as I said, it feels like, why did we even bother giving it a name? But it is so useful not to study linear combinations on their own, but to study things that are well behaved around linear combinations. That is such a useful thing that there's an entire semester course in undergraduate mathematics that is the study of those things. Linear algebra, if anyone is going onward in that direction. Linear algebra is perhaps the most useful mathematics course that exists. If you are going into math, natural sciences, computer science, economics, finance, it is impossible to know too much linear algebra. The more linear algebra you know, the more useful it will become. Right. That's enough for my advertisement there. Let's look at a different way of combining functions. All right. The composition of two functions f and g is denoted using a circle argument. All right, so much like you can take the dot product, right? If you have two numbers you're multiplying together, a dot b, you can take the circle of two functions, f circle g. Right? It kind of looks like it just says fog, but that is a circle operator, which is different from the letter O, right? The letter O, larger and baselined, capital O, taller and baselined. The circle function is small and centered on the line. So if you're looking at writing between a couple of lines, lowercase o, circle function, capital O. Right. So evaluating a function as a composition is something you've seen in the past. That's not what I'm interested in. Much like in our discussion of linear combinations, I'm mostly interested in, if you are given something that is compound, can you recognize and deconstruct it into the composition of two functions? So for example, if we're looking at h of x is the square root of 9 minus x squared, we can recognize that this is a composition of the square root and g of x being the stuff inside the square root, 9 minus x squared. If you take f of x, f composed with g of x is f of g of x, which is f of 9 minus x squared. And since f is the square root, that's the square root of 9 minus x squared. All right, being able to expand out given two functions and their composition is something that you should already be familiar with coming into this course. Again, my goal for you is to look the other way. When you see the square root of 9 minus x squared, you can deconstruct it and say that this is the composition of square root and 9 minus x squared. It's one of several different ways that you can deconstruct it. This particular one is the most useful. As a general rule, we're looking for different kinds of functions. So square root of x is a square root function. 9 minus x squared is a polynomial function. And having the simplest square root function makes things easier. But the specifics of which version you should use is something we'll talk about in the future. As another example, if we have some sort of fraction going on, three over 4x plus 7, you should be able to notice that if we take f of x as 3 over x and g of x as 4x plus 7, then h of x is f composed with g of x. All right, one more to look at. H of x is the absolute value of 4 minus x squared. Compared to the ones that we were just looking at, this one is fairly straightforward. But we can decompose this as f of x equals the absolute value of x, and g of x is 4 minus x squared. That's not too tricky. But before I move on, I wanted to look at this because specifically compositions like this involving absolute value are going to be something that is a little bit challenging to work with as we move forward. So I want to just keep looking at h of x is the absolute value of 4 minus x squared. I said that I would decompose this and let f of x be the absolute value of x. And you should remember from a previous video that the absolute value of x is defined as the piecewise function, where it's equal to x if x is greater than or equal to 0, and it's equal to the opposite of x if x is less than 0. And so, by evaluating this at another argument, that means that the absolute value of 4 minus x squared should be equal to the piecewise defined function 4 minus x squared if 4 minus x squared is greater than or equal to 0, and the opposite of 4 minus x squared if 4 minus x squared is less than 0. I'm going to come back and clean this up a bit. But just by knowing this, that should give us enough tools to play around with and graph the function y equals h of x. Instead of trying to do that by hand, I am going to jump over to Desmos, where you can see here that I have in blue graphed 4 minus x squared. There we go. In blue graphed 4 minus x squared. I have the opposite of 4 minus x squared not yet graphed. The circle over here is left empty. And then absolute value, which Desmos reads as ABS instead of using the vertical bars. All right, but here's the graph of 4 minus x squared. When 4 minus x squared is greater than 0, absolute value uses exactly this graph. So we can look at this and say, okay, let's just take this part here that is bigger than 0, and that's going to be part of the graph. The other part of the graph is going to be determined based on when the negative, which is now graphed using a light blue dotted line. Notice that this thing is positive over here on this extreme, and over here on this extreme, and negative down here in the middle. And again, the piecewise defined function only cares about what happens when this thing is positive. So it makes sense when I try to graph absolute value, which is now done in orange. And let's move that so it's on top of everything else. There we go. Now that that's done in orange, you can see that it takes the positive branch of both pieces. So just by thinking about what an absolute value does and thinking about how the composition with absolute value works, you can reason through how to graph this thing without having to rely on piece by piece. But while we're at it, we can also deal with this thing piece by piece. So let's get away from the graph and back to the definition of the function here. 4 minus x squared is done. There's not really anything else I can do with that. 4 minus x squared greater than or equal to 0, that's an inequality that I should be able to solve. And then 4 minus x squared less than 0 is the complement of that. We should be able to work with those things together. And I'll also point out that the opposite of 4 minus x squared is something pretty easy to deal with. Let's jump into that right away. The opposite of 4 minus x squared, the opposite of subtraction is subtraction in the other order. So this is x squared minus 4, just a simple way to clean things up a little bit. The inequality is what I really care about. To solve a nonlinear inequality you've probably learned in the past, ignore the inequality symbol and set it up as an equality. Solve that equality. And then plot those points on a number line. Then pick some values in between. The theory here is that the only way to go from being less than 0 to greater than 0, or from greater than 0 to less than 0, is to pass through being equal to 0. So we have marked the places where this equation is equal to 0, and if we test any one point in the regions that that divides the number line into, which are directly behind me right now, but the truth at any one point will be the truth for the entire region. So that's why we pick -3. If I evaluate 4 minus -3 squared, I get 4 minus 9, which is -5, which is clearly less than 0. If I plug in x equals 0, I get 4, which is clearly greater than 0. If I plug in 3, I get -5 again, which is again less than 0. So from that, 4 minus x squared greater than 0 is equivalent to -2 less than x less than 2. This stuff in this region. Now, in our original function here, we have actually 4 minus x squared is greater than or equal to 0. And since equal to 0 happens at both of those endpoints, that just means we're going to put those endpoints in. If the inequality involved fractions, you might have to worry about an endpoint being undefined, but that didn't happen here, so one less thing to worry about. And then the other option we cared about was 4 minus x squared less than 0, which happens in two places. It happens over here, where x is less than -2, and it happens when x is greater than +2 in both of those places. Why did I write a 4 over there? All the changes happen at +2 and at -2. All right, so with that, our function absolute value of 4 minus x squared is a piecewise defined function with 3 pieces. It is x squared minus 4 if x is less than -2, 4 minus x squared if -2 is less than or equal to x is less than or equal to 2, and it's again x squared minus 4 if x is greater than +2. Right, here's one for you to try. I'd like you to take a look at the function f of x equals the absolute value of x over 1 minus x. So I would like you to graph this function. And then after you have graphed the function using Desmos or something like that, see if you can go through what I just did and write this as a piecewise defined function. Right, with that, I'll wrap up here. Thank you as always for joining me, and I'll see you in the next video.